Today's topic is going to be Faraday's law. This will be the fourth of the four Maxwell equations that we discuss. This is a very important law, has a lot of applications in real life, and so without any further ado, let's give it a sort of a top view description. First thing is to say that Faraday's law deals with changing magnetic fields or changing magnetic fluxes, and the fact that they can cause electromotive forces, induced EMFs, and electric fields. So let's talk about that. First thing is, we can, as you can imagine, you can create a magnetic field with a current. If you vary that current, you'll vary the magnetic field in time. What Faraday was able to show, Faraday and Henry independently were able to show, is that if I have a changing magnetic field, an EMF can be induced in a circuit. And it's almost like magic. You don't need a battery there. All you need is a changing magnetic field, and you'll actually measure a current and a voltage. As I said, Faraday and Joseph Henry did these experiments independently. The law, though, is named after Faraday. Henry gets the consolation prize by having a unit of inductance named after him, but that's in the next chapter. So we can talk about this induced EMF, and we're able to find the value of the induced EMF from the changing magnetic field using Faraday's law. So first off, let's talk about Michael Faraday. He was a British physicist and chemist, did some great work in experimental chemistry and physics, is credited with inventing the motor, the generator, transformer, did the laws of electrolysis in chemistry. We talk about electrochemistry, a lot of that is credited to Faraday. And then, of course, electromagnetic induction, which is the topic for today. Let's set this up. Of course, Faraday didn't have digital multimeters in his day, but we can talk about a modern version of the Faraday's law experiment. What happens is this. If I take a simple bar magnet and I push that bar magnet through a loop of wire, what is going to happen is that the ammeter, we're going to use our multimeter as an ammeter, is going to register a current. And if I were to pull it in the other direction, I would find that the value of the current would be the opposite. So if it were a negative current in one direction, it would be a positive current in the other direction. This is pretty amazing. As I say, there are no batteries or anything. And so, but one of the interesting aspects about this is if I were to just hold the magnet inside the coil of wire, that would have no effect whatsoever. And so what this led Faraday to understand is that it's not the presence of the magnet that causes the current or the EMF, both. It's the fact that the magnetic field changes. I have to move the magnet toward the coil or move the magnet away from the coil to induce this EMF. So it's a changing magnetic field, or as it turns out, a changing magnetic flux that will cause this effect. As I say, if you move it away from the coil, we get the opposite. So you see a deflection going in the positive direction for the current. So once again, to sum, if I take the coil, I move it toward the wire, I get a negative current. If I hold it steady in there, I get 0. And then as I pull it out of the loop, I get a positive current. And so this is, in a sense, Faraday's law. What Faraday did, of course, is to quantify what size of current or EMF is produced when I cause this change in magnetic field or magnetic flux. There's a second experiment that Faraday did, which is also kind of interesting. What he did is he connected a battery to a coil of wire and wrapped it around an iron ring. Now, the iron ring is only used to magnify the effects, otherwise it would be much too small. But the iron ring itself isn't causing this effect to happen, it's just making it look larger. But in this case, you have a coil of wire that will eventually be connected with a battery, and you have a second, what we call a secondary coil of wire that's connected to an ammeter. Now, of course, because there's no connection between these two wires, probably the assumption would be, well, there's no connection, therefore nothing should happen when I connect this wire to a battery, because there isn't any kind of connection that we can see between these coils of wire. But of course, that's not correct. In fact, as soon as the battery is engaged and a current runs through the first wire, we're going to find that we get a current through the second wire. And of course, that's because when I run the current through the first wire using the battery, I'm creating a magnetic field. I've gone from zero magnetic field to some magnetic field. That changing magnetic field is what induces an EMF and a current in that secondary coil. Pretty amazing when you think about it, but this is how electromagnetism works. So what does he find? As soon as he closes the switch, engages the battery, the ammeter changes from 0 in one direction, but then it returns to 0, because if I keep the switch completely closed and do nothing else, there will be no more deflection. Once I open the switch, remove the battery, that is to say, from the circuit, ammeter is going to change in the opposite direction. Again, because now I've gone from a magnetic field produced in the primary coil to zero magnetic field produced in the primary coil. That change in magnetic field is what causes the secondary wire and the secondary, the ammeter that's attached to the secondary wire to read a non-zero current. So, what do we conclude from all of this? Well, first of all, I can induce an electric current in a secondary loop just by changing a magnetic field, whether it's using a bar magnet or putting a current through a primary coil and inducing the field in a secondary current in a secondary coil. While the field is changing, I get the current. When the field is constant, I get zero current. And so what we say is that an induced EMF is produced in the secondary loop by a changing magnetic field. To be more precise, it's not just a changing magnetic field, but it's a changing magnetic flux. And we'll show some examples of that as well. Quantitatively, we write Faraday's law very simply as the induced EMF in a circuit is equal to the time derivative of the magnetic flux. So indeed, if it's not just a changing field, it could be a changing area element also, even if the field is constant. That would cause this changing magnetic flux. The changing magnetic flux is what causes this induced EMF. To be more exact, if I have n loops of wire, all of the same area, then I can write my induced EMF is equal to n times the time derivative of the magnetic flux. Notice there's a negative sign in there. We're going to talk about that. That is a non-trivial negative sign that just kind of keep in the back of our mind for now. We'll talk about why it has to be that way in a little bit. So suppose I have a loop that encloses some area A. The magnetic flux through the loop is B times A times the cosine of the angle, if the field happens to be a constant, that is. B times A times the cosine of the angle between the magnetic field and, of course, the area vector, which is always perpendicular to the loop. So I can write the induced EMF is the time derivative, or the negative time derivative, of B times A times cosine theta. That tells you that one of three things can cause an induced EMF. You can change the magnetic field with time, you can change the area of the loop with time, and of course you can change the angle between the field and the loop. Any one of those things that happens will cause an induced EMF. Some applications of this, some real world applications, is the ground fault interrupter. This is what the safety device that's used in bathrooms and kitchens most often. If you have all of a sudden a short circuit, it will take the power out of the circuit, and so that nobody will be endangered by the excess of current. So typically the way this works is, if I have currents in the wire in opposite directions, I have a net magnetic flux of 0. But if all of a sudden, for some reason, I have a short circuit or some other malfunction, if the current in the wire coming out changes, if it becomes greater than 0, now my magnetic flux is no longer 0. That's going to induce an EMF in my ground fault interrupter, and that's going to trigger the circuit breaker and stop the current from flowing, which of course can save somebody from a really bad shock. So that's one nice use for where Faraday's law applies. Another one is one particularly close to my heart, and that is how we can use Faraday's law to talk about the pickup coil in an electric guitar. So how does an electric guitar work? First of all, I have to ask you, have you ever heard an electric guitar played with no amplifier? It sounds pretty awful. In fact, it sounds kind of like metal clothes hangers hitting one another. So how come electric guitars sound so good? Well, because we can not only produce a nice sound, but we can amplify it as well. And this is how it works. So electric guitars have pickup coils. My Fender has 3 pickup coils in it. What they are, the coil will be placed near one of the vibrating strings. When the string vibrates, because it's a metal string, it's going to magnetize a portion of the string. When it vibrates at some frequency, that's producing a changing magnetic field. And that changing magnetic field, of course, yields a changing magnetic flux, which causes an EMF. The EMF and the current is very small at that point, but what you do is you feed that signal to an amplifier, and the amplifier will greatly enhance that value, and of course you have a much stronger signal. Now that's not the end of the story, although that's the end of the story on this slide. The end of the story is you can't hear it unless the signal is sent to a speaker. What the speaker does is it transduces that electrical signal into an acoustic wave, a pressure wave, and of course the speaker will vibrate, producing a pressure wave that your ear can perceive. So that's why you hear this nice sound of an electric guitar, as opposed to just kind of a teeny little vibrating string. Very nice application of Faraday's law. Another application, also very nice, is this notion of motional EMF. So if I have a conductor moving through a constant magnetic field, the electrons in the conductor, of course, are going to experience a force, QV cross B, that's directed along the length. That force will cause the field to change. That motion will cause the electrons to move to the lower end of the conductor and accumulate there. when the charges separate, an electric field is produced, and we have the charges accumulating at both ends of the conductor till they're in equilibrium. And then what we have is a case where the electrostatic force and the magnetic force are equal to one another. And then we can talk about the fact that the potential difference can be, or the induced EMF would be equal to E times L, electric field times the length, or, if you like, the magnetic field times the length times the velocity of the charges. And so as long as the conductor moves through the magnetic field, you'll continue to maintain the potential difference. Of course, if we change the motion, we change the polarity of the EMF that's induced. Really nice picture of this is in the following slide. Notice we have two conducting rails and a conducting bar across those rails. We put this device in a constant magnetic field that's going into the screen. And what's going to happen is if I slide my conducting bar to the right at some velocity v, that's going to cause an increase in the magnetic flux, because the field is constant, but the area of the field that's encompassed by the bar and the two rails and this line here will be larger. So because the field is going up, because the field is constant, but the area is increasing, the flux increases, that change in flux is going to cause an EMF, and thus a current to go through the circuit. So this is what we call motional EMF. There's a very simple expression for how that works. In this case, we can say the following. I can write the EMF that's induced as we'll just write it, minus the magnetic flux, change in magnetic flux over time. In this case, that's going to be equal to, the field is constant, but the area is changing, so that would be the magnetic field times the change in area with respect to time. That's going to be equal to minus the, so that's going to be the length times the change in width divided by change in time. My change in width divided by time is just the velocity at which that bar is moving to the right. And so that's going to be minus b times L times v. So this is a very, very simple expression for motional EMF. And by the way, that's going to also induce a current in this circuit. You see we have a resistor over to the left. The current that's induced is going to be equal to minus b LV divided by the value of that resistance, just by Ohm's law. And so this is a really nice way of describing motional EMF. On the other hand, were I to move the bar towards the left, that would cause a decrease in magnetic flux, and that would give me an opposite sign value for my EMF and my current that's induced. The question becomes, where did that minus sign come from, and why do we have it there at all? Let's talk about some of the ramifications of this. So suppose we reproduce that diagram. So we have a resistor here. We've got two conducting rails and a conducting bar. We have a magnetic field going into the board. And let's say we move this guy with a velocity v to the right. And this is some length, call that L. We said that the motional EMF is equal to minus VLD. So we want to find the direction of the current going through the circuit. So there's a law of physics called Lenz's law. Lenz's law says that nature abhors a change in magnetic flux, and it will produce a magnetic field and current that will oppose that change in magnetic flux. So let me show you how that works. This is where the minus sign comes from. So if I move this rail to the right, increase the flux, nature says I don't want an increase in flux. So what it will do is to induce a magnetic field that comes out of the board. So if the original field is going into the board, by moving this rail to the right, moving this bar to the right, I'm going to induce a magnetic field that comes out of the board. Therefore, that means in order to induce a field that comes out of the board, I would have to have a current that's going counterclockwise according to the right-hand rule. So what's going to happen is when I move this guy to the right, I'm going to induce a current that's going counterclockwise or down through that resistor and around the circuit. It's what we call Lenz's law. On the other hand, if I were to move this bar to the left, in that case, I would be decreasing the magnetic flux. Nature opposes that decrease as much as it would oppose the increase from before. It's going to want a magnetic field that goes into the board to compensate for this attempt to decrease the magnetic flux. That being the case, it would induce a current that's going clockwise around the circuit to compensate for the decreasing flux. And this is how Lenz's law works. And you might say, why does it work that way? Well, the best way to explain that is with energy considerations. Suppose it didn't. Let's pretend that Lenz's law works in the opposite way. Suppose I'm moving the bar to the right. If I move the bar to the right, notice what will happen. If what we got was a current that went, instead of going counterclockwise to get the field coming, suppose it were going the other way, suppose it were going into the board. So if I induced a field into the board, notice what would happen. I have a field going into the board. I have a current going, let's look at this rail. In this way, if it's going clockwise, it would be going downwards. So the current is going into, so the field is going into the board. The current is going downwards. The magnetic force on this bar would be in this direction. That means it would tend to move this bar faster and faster and faster in this direction, which would give it more and more and more kinetic energy for nothing. In other words, I've either found some discovery that would make me billions of dollars, or what I've done is violate a law of physics. In other words, the conservation of energy. This can't happen. If it were true that the current would go counterclockwise, that would cause this bar to accelerate to the right with no effort. Not allowed. Physics doesn't allow such a thing. Therefore, it's sort of a proof by contradiction. So we know then that what's going to happen is the field is going to go counterclockwise to resist this change in magnetic flux. And so that saves one of the important laws in physics. in it, we'll continue this in our next lecture.